Mars is the fourth planet from the Sun and the second smallest planet in the Solar System after Mercury. In English, Mars carries a name of the Roman god of war, and is often referred to as the Red Planet, because the iron oxide prevalent on its surface gives it a reddish appearance that is distinctive among the astronomical bodies visible to the naked eye. Mars is a terrestrial planet with a thin atmosphere, having surface features reminiscent both of the impact craters of the Moon and the valleys, deserts, and polar ice caps of Earth. The days and seasons are likewise comparable to those of Earth, because the rotational period as well as the tilt of the rotational axis relative to the ecliptic plane are very similar. Mars is the site of Olympus Mons, the largest volcano and second highest known mountain in the Solar System, and of Valles Marineris, one of the largest canyons in the Solar System. The smooth Borealis Basin in the Northern Hemisphere covers 40% of the planet and may be a giant impact feature. Mars has two moons, Phobos and Deimos, which are small and irregularly shaped. These may be captured asteroids, similar to 5261 Eureka, a Mars Trojan. There are ongoing investigations assessing the past habitability potential of Mars, as well as the possibility of extant life. Future astrobiology missions are planned, including the Mars 2020 and ExoMars rovers. Liquid water cannot exist on the surface of Mars due to low atmospheric pressure, which is less than 1% of the Earth's, except at the lowest elevations for short periods. The two polar ice caps appear to be made largely of water. The volume of water ice in the south polar ice cap, if melted, would be sufficient to cover the entire planetary surface to a depth of 11 meters (36 feet). In November 2016, NASA reported finding a large amount of underground ice in the Utopia Planitia region of Mars. The volume of water detected has been estimated to be equivalent to the volume of water in Lake Superior. Mars can easily be seen from Earth with the naked eye, as can its reddish coloring. Its apparent magnitude reaches -2.94, which is surpassed only by Jupiter, Venus, the Moon, and the Sun. Optical ground-based telescopes are typically limited to resolving features about 300 kilometers (190 miles) across when Earth and Mars are closest because of Earth's atmosphere. Topic: Physical characteristics. Mars is approximately half the diameter of Earth, with a surface area only slightly less than the total area of Earth's dry land. Mars is less dense than Earth, having about 15% of Earth's volume and 11% of Earth's mass, resulting in about 38% of Earth's surface gravity. The red-orange appearance of the Martian surface is caused by iron oxide, or rust. It can look like butterscotch. Other common surface colors include golden, brown, tan, and greenish, depending on the minerals present. Topic: Internal structure. Like Earth, Mars has differentiated into a dense metallic core overlaid by less dense materials. Current models of its interior imply a core with a radius of about 1,794 plus or minus 65 kilometers, 1,115 plus or minus 40 miles, consisting primarily of iron and nickel with about 16 to 17% sulfur. This iron, sulfide core is thought to be twice as rich in lighter elements as Earth's. The core is surrounded by a silicate mantle that formed many of the tectonic and volcanic features on the planet, but it appears to be dormant. Besides silicon and oxygen, the most abundant elements in the Martian crust are iron, magnesium, aluminum, calcium, and potassium. The average thickness of the planet's crust is about 50 kilometers (31 miles), with a maximum thickness of 125 kilometers (78 miles). Earth's crust averages 40 kilometers (25 miles). Topic: Surface geology. Mars is a terrestrial planet that consists of minerals containing silicon and oxygen, metals, and other elements that typically make up rock. The surface of Mars is primarily composed of tholeiitic basalt, although parts are more silica-rich than typical basalt and may be similar to andesitic rocks on Earth or silica glass. Regions of low albedo suggest concentrations of plagioclase feldspar, with northern low albedo regions displaying higher than normal concentrations of sheet silicates and high silicon glass. Parts of the southern highlands include detectable amounts of high calcium pyroxenes. Localized concentrations of hematite and olivine have been found. Much of the surface is deeply covered by finely grained iron oxide dust. Although Mars has no evidence of a structured global magnetic field, observations show that parts of the planet's crust have been magnetized, suggesting that alternating polarity reversals of its dipole field have occurred in the past. This paleomagnetism of magnetically susceptible minerals is similar to the alternating bands found on Earth's ocean floors. One theory, published in 1999 and re-examined in October 2005 with the help of the Mars Global Surveyor, is that these bands suggest plate tectonic activity on Mars 4 billion years ago, before the planetary dynamo ceased to function and the planet's magnetic field faded. It is thought that, during the Solar System's formation, Mars was created as the result of a stochastic process of runaway accretion of material from the protoplanetary disk that orbited the Sun. Mars has many distinctive chemical features caused by its position in the Solar System. Elements with comparatively low boiling points, such as chlorine, phosphorus, and sulfur, are much more common on Mars than Earth. These elements were probably pushed outward by the young Sun's energetic solar wind. After the formation of the planets, all were subjected to the so-called late heavy bombardment. About 60% of the surface of Mars shows a record of impacts from that era, whereas much of the remaining surface is probably underlain by immense impact basins caused by those events. There is evidence of an enormous impact basin in the northern hemisphere of Mars, spanning 10,600 by 8,500 kilometers, 6,600 by 5,300 miles, or roughly 4 times the size of the Moon's south pole. Aitken Basin, the largest impact basin yet discovered. This theory suggests that Mars was struck by a Pluto-sized body about 4 billion years ago. The event, thought to be the cause of the Martian hemispheric dichotomy, created the smooth Borealis basin that covers 40% of the planet. The geological history of Mars can be split into many periods, but the following are the 3 primary periods. Noachian period, named after Noach's Terra, formation of the oldest extant surfaces of Mars, 4.5 to 3.5 billion years ago. Noachian-age surfaces are scarred by many large impact craters. The Tharsis Bulge, a volcanic upland, is thought to have formed during this period, with extensive flooding by liquid water late in the period. Hesperian period, named after Hesperia planum, 3.5 to between 3.3 and 2.9 billion years ago. The Hesperian period is marked by the formation of extensive lava plains. Amazonian period, named after Amazonas Planitia, between 3.3 and 2.9 billion years ago to the present. Amazonian regions have few meteorite impact craters, but are otherwise quite varied. Olympus Mons formed during this period, with lava flows elsewhere on Mars. Geological activity is still taking place on Mars. The Athabasca Valles is home to sheet-like lava flows created about 200 Maya. Water flows in the grabens called the Cerberus fossae occurred less than 20 Maya, indicating equally recent volcanic intrusions. On February 19, 2008, images from the Mars Reconnaissance Orbiter showed evidence of an avalanche from a 700-meter-high (2,300 feet) cliff. Soil. The Phoenix lander returned data showing Martian soil to be slightly alkaline and containing elements such as magnesium, sodium, potassium and chlorine. These nutrients are found in soils on Earth, and they are necessary for growth of plants. Experiments performed by the lander showed that the Martian soil has a basic pH of 7.7, and contains 0.6% of the salt perchlorate. This is a very high concentration and makes the Martian soil toxic. See also Martian soil toxicity. Streaks are common across Mars and new ones appear frequently on steep slopes of craters, troughs, and valleys. The streaks are dark at first and get lighter with age. The streaks can start in a tiny area, then spread out for hundreds of meters. They have been seen to follow the edges of boulders and other obstacles in their path. The commonly accepted theories include that they are dark underlying layers of soil revealed after avalanches of bright dust or dust devils. Several other explanations have been put forward, including those that involve water or even the growth of organisms. Hydrology. Liquid water cannot exist on the surface of Mars due to low atmospheric pressure, which is less than 1% that of Earth's, except at the lowest elevations for short periods. The two polar ice caps appear to be made largely of water. The volume of water ice in the south polar ice cap, if melted, would be sufficient to cover the entire planetary surface to a depth of 11 meters (36 feet). A permafrost mantle stretches from the pole to latitudes of about 60 degrees. Large quantities of water ice are thought to be trapped within the thick cryosphere of Mars. Radar data from Mars Express and the Mars Reconnaissance Orbiter show large quantities of water ice at both poles, July 2005, and at middle latitudes, November 2008. The Phoenix lander directly sampled water ice in shallow Martian soil on July 31, 2008. Landforms visible on Mars strongly suggest that liquid water has existed on the planet's surface. Huge linear swaths of scoured ground, known as outflow channels, cut across the surface in about 25 places. These are thought to be a record of erosion caused by the catastrophic release of water from subsurface aquifers, though some of these structures have been hypothesized to result from the action of glaciers or lava. One of the larger examples, M'Adam Vallis, is 700 kilometers (430 miles) long, much greater than the Grand Canyon, with a width of 20 kilometers (12 miles) and a depth of 2 kilometers (1.2 miles) in places. It is thought to have been carved by flowing water early in Mars's history. The youngest of these channels are thought to have formed as recently as only a few million years ago. Elsewhere, particularly on the oldest areas of the Martian surface, finer scale, dendritic networks of valleys are spread across significant proportions of the landscape. Features of these valleys and their distribution strongly imply that they were carved by runoff resulting from precipitation in early Mars history. Subsurface water flow and groundwater sapping may play important subsidiary roles in some networks, but precipitation was probably the root cause of the incision in almost all cases. Along crater and canyon walls, there are thousands of features that appear similar to terrestrial gullies. The gullies tend to be in the highlands of the southern hemisphere and to face the equator. All are poleward of 30 degrees latitude. A number of authors have suggested that their formation process involves liquid water, probably from melting ice, although others have argued for formation mechanisms involving carbon dioxide frost or the movement of dry dust. No partially degraded gullies have formed by weathering and no superimposed impact craters have been observed, indicating that these are young features, possibly still active. Other geological features, such as deltas and alluvial fans preserved in craters, are further evidence for warmer, wetter conditions at an interval or intervals in earlier Mars history. Such conditions necessarily require the widespread presence of crater lakes across a large proportion of the surface, for which there is independent mineralogical, sedimentological and geomorphological evidence. Further evidence that liquid water once existed on the surface of Mars comes from the detection of specific minerals such as hematite and goethite, both of which sometimes form in the presence of water. In 2004, Opportunity detected the mineral jarosite. This forms only in the presence of acidic water, which demonstrates that water once existed on Mars. More recent evidence for liquid water comes from the finding of the mineral gypsum on the surface by NASA's Mars rover Opportunity in December 2011. It is estimated that the amount of water in the upper mantle of Mars, represented by hydroxyl ions contained within the minerals of Mars's geology, is equal to or greater than that of Earth at 50 to 300 parts per million of water, which is enough to cover the entire planet to a depth of 200 to 1,000 meters (660 to 3,280 feet). In 2005, radar data revealed the presence of large quantities of water ice at the poles and at mid-latitudes. The Mars rover Spirit sampled chemical compounds containing water molecules in March 2007. The Phoenix lander directly sampled water ice in shallow Martian soil on July 31, 2008. On March 18, 2013, NASA reported evidence from instruments on the Curiosity rover of mineral hydration, likely hydrated calcium sulfate, in several rock samples including the broken fragments of Tintina rock and Sutton-Inlier rock, as well as in veins and nodules in other rocks like Knorr rock and Wernick rock. Analysis using the rover's DAN instrument provided evidence of subsurface water, amounting to as much as 4% water content, down to a depth of 60 centimeters (24 in), during the rover's traverse from the Bradbury landing site to the Yellowknife Bay area in the Glenelg terrain. In September 2015, NASA announced that they had found conclusive evidence of hydrated brine flows on recurring slope lineae, based on spectrometer readings of the darkened areas of slopes. These observations provided confirmation of earlier hypotheses based on timing of formation and their rate of growth, that these dark streaks resulted from water flowing in the very shallow subsurface. The streaks contain hydrated salts, perchlorates, which have water molecules in their crystal structure. The streaks flow downhill in Martian summer, when the temperature is above -23 degrees Celsius, and freeze at lower temperatures. On September 28, 2015, NASA announced the presence of briny flowing salt water on the Martian surface. Researchers suspect that much of the low northern plains of the planet were covered with an ocean hundreds of meters deep, though this remains controversial. In March 2015, scientists stated that such an ocean might have been the size of Earth's Arctic Ocean. This finding was derived from the ratio of water to deuterium in the modern Martian atmosphere compared to that ratio on Earth. The amount of Martian deuterium is 8 times the amount that exists on Earth, suggesting that ancient Mars had significantly higher levels of water. Results from the Curiosity rover had previously found a high ratio of deuterium in Gale Crater, though not significantly high enough to suggest the former presence of an ocean. Other scientists caution that these results have not been confirmed, and point out that Martian climate models have not yet shown that the planet was warm enough in the past to support bodies of liquid water. Near the northern polar cap is the 81.4 kilometers (50.6 miles) wide Korolyov crater, where the Mars Express orbiter found it to be filled with approximately 2,200 cubic kilometers (530 cubic miles) of water ice. The crater floor lies about 2 kilometers (1.2 miles) below the rim, and is covered by a 1.8 kilometers (1.1 miles) deep central mound of permanent water ice, up to 60 kilometers (37 miles) in diameter. Polar caps. Mars has two permanent polar ice caps. During a pole's winter, it lies in continuous darkness, chilling the surface and causing the deposition of 25 to 30% of the atmosphere into slabs of CO2 ice, dry ice. When the poles are again exposed to sunlight, the frozen CO2 sublimes. These seasonal actions transport large amounts of dust and water vapor, giving rise to Earth-like frost and large cirrus clouds. Clouds of water ice were photographed by the Opportunity rover in 2004. The caps at both poles consist primarily 70% of water ice. Frozen carbon dioxide accumulates as a comparatively thin layer about 1 meter thick on the North Cap in the northern winter only, whereas the South Cap has a permanent dry ice cover about 8 meters thick. This permanent dry ice cover at the South Pole is peppered by flat-floored, shallow, roughly circular pits, which repeat imaging shows are expanding by meters per year. This suggests that the permanent CO2 cover over the South Pole water ice is degrading over time. The northern polar cap has a diameter of about 1,000 kilometers (620 miles) during the northern Mars summer, and contains about 1.6 million cubic kilometers (380,000 cubic miles) of ice, which, if spread evenly on the cap, would be 2 kilometers (1.2 miles) thick. This compares to a volume of 2.85 million cubic kilometers (680,000 cubic miles) for the Greenland ice sheet. The southern polar cap has a diameter of 350 kilometers (220 miles) and a thickness of 3 kilometers (1.9 miles). The total volume of ice in the South Polar Cap plus the adjacent layered deposits has been estimated at 1.6 million cubic km. Both polar caps show spiral troughs, which recent analysis of Sherrod ice-penetrating radar has shown are a result of katabatic winds that spiral due to the Coriolis effect, the seasonal frosting of areas near the southern ice cap results in the formation of transparent 1-meter thick slabs of dry ice above the ground. With the arrival of spring, sunlight warms the subsurface and pressure from subliming CO2 builds up under a slab, elevating and ultimately rupturing it. This leads to geyser-like eruptions of CO2 gas mixed with dark basaltic sand or dust. This process is rapid, observed happening in the space of a few days, weeks or months, a rate of change rather unusual in geology, especially for Mars. The gas rushing underneath a slab to the site of a geyser carves a spiderweb-like pattern of radial channels under the ice, the process being the inverted equivalent of an erosion network formed by water draining through a single plug hole. Geography and naming of surface features. Although better remembered for mapping the Moon, Johann Heinrich Madler and Wilhelm Beer were the first areographers. They began by establishing that most of Mars's surface features were permanent and by more precisely determining the planet's rotation period. In 1840, Madler combined 10 years of observations and drew the first map of Mars. Rather than giving names to the various markings, Beer and Madler simply designated them with letters. Meridian Bay, Sinus Meridiani, was thus feature A. Today, features on Mars are named from a variety of sources. Albedo features are named for classical mythology. Craters larger than 60 kilometers are named for deceased scientists and writers and others who have contributed to the study of Mars. Craters smaller than 60 kilometers are named for towns and villages of the world with populations of less than 100,000. Large valleys are named for the word Mars or star. In various languages, small valleys are named for rivers. Large albedo features retain many of the older names, but are often updated to reflect new knowledge of the nature of the features. For example, Nix Olympica, the snows of Olympus, has become Olympus Mons, Mount Olympus. The surface of Mars as seen from Earth is divided into two kinds of areas, with differing albedo. The paler plains covered with dust and sand rich in reddish iron oxides were once thought of as Martian continents, and given names like Arabia Terra, Land of Arabia, or Amazonas Planitia, Amazonian Plain. The dark features were thought to be seas, hence their names Mare Erythraeum, Mare Sirenum and Aurore Sinus. The largest dark feature seen from Earth is Syrtis Major Planum. The permanent northern polar ice cap is named Planum boreum, whereas the southern cap is called Planum australe. Mars's equator is defined by its rotation, but the location of its prime meridian was specified, as was Earth's, at Greenwich, by choice of an arbitrary point. Madler and Beer selected a line for their first maps of Mars in 1830. After the spacecraft Mariner 9 provided extensive imagery of Mars in 1972, a small crater, later called Ares 0, located in the Sinus Meridiani, Middle Bay, or Meridian Bay, was chosen for the definition of 0.0 degrees longitude to coincide with the original selection, because Mars has no oceans and hence no sea level. A zero-elevation surface had to be selected as a reference level. This is called the areoid of Mars, analogous to the terrestrial geoid. Zero altitude was defined by the height at which there is 610.5 pascals, 6.105 millibars of atmospheric pressure. This pressure corresponds to the triple point of water, and it is about 0.6% of the sea level surface pressure on Earth, 0.006 atmospheres. In practice, today this surface is defined directly from satellite gravity measurements. Topic: Map of quadrangles. For mapping purposes, the United States Geological Survey divides the surface of Mars into 30 cartographic quadrangles, each named for a classical albedo feature it contains. The quadrangles can be seen and explored via the interactive image map below. Topic: Impact topography. The dichotomy of Martian topography is striking. Northern plains flattened by lava flows contrast with the southern highlands, pitted and cratered by ancient impacts. Research in 2008 has presented evidence regarding a theory proposed in 1980 postulating that, 4 billion years ago, the northern hemisphere of Mars was struck by an object 1/10 to 2/3 the size of Earth's moon. If validated, this would make the northern hemisphere of Mars the site of an impact crater 10,600 by 8,500 kilometers, 6,600 by 5,300 miles in size, or roughly the area of Europe, Asia, and Australia combined, surpassing the South Pole Aitken Basin as the largest impact crater in the Solar System. Mars is scarred by a number of impact craters, a total of 43,000 craters with a diameter of 5 kilometers (3.1 miles) or greater have been found. The largest confirmed of these is the Hellas Impact Basin, a light albedo feature clearly visible from Earth. Due to the smaller mass of Mars, the probability of an object colliding with the planet is about half that of Earth. Mars is located closer to the asteroid belt, so it has an increased chance of being struck by materials from that source. Mars is more likely to be struck by short-period comets, i.e., those that lie within the orbit of Jupiter. In spite of this, there are far fewer craters on Mars compared with the Moon, because the atmosphere of Mars provides protection against small meteors and surface-modifying processes have erased some craters. Martian craters can have a morphology that suggests the ground became wet after the meteor impacted. Topic: Volcanoes. The shield volcano Olympus Mons, Mount Olympus, is an extinct volcano in the vast upland region Tharsis, which contains several other large volcanoes. Olympus Mons is roughly 3 times the height of Mount Everest, which in comparison stands at just over 8.8 kilometers, 5.5 miles. It is either the tallest or second tallest mountain in the Solar System, depending on how it is measured, with various sources giving figures ranging from about 21 to 27 kilometers, 13 to 17 miles high. Topic: Tectonic sites. The large canyon, Valles Marineris, Latin for Mariner Valleys, also known as Agathodiman in the old canal maps, has a length of 4,000 kilometers (2,500 miles) and a depth of up to 7 kilometers (4.3 miles). The length of Valles Marineris is equivalent to the length of Europe and extends across 1/5 the circumference of Mars. By comparison, the Grand Canyon on Earth is only 446 kilometers (277 miles) long and nearly 2 kilometers (1.2 miles) deep. Valles Marineris was formed due to the swelling of the Tharsis area, which caused the crust in the area of Valles Marineris to collapse. In 2012, it was proposed that Valles Marineris is not just a graben, but a plate boundary where 150 kilometers (93 miles) of transverse motion has occurred, making Mars a planet with possibly a 2 tectonic plate arrangement. Topic: Poles. Images from the Thermal Emission Imaging System (THEMIS) aboard NASA's Mars Odyssey orbiter have revealed 7 possible cave entrances on the flanks of the volcano Arsia Mons. The caves, named after loved ones of their discoverers, are collectively known as the Seven Sisters Cave entrances measure from 100 to 252 meters (328 to 827 feet) wide, and they are estimated to be at least 73 to 96 meters (240 to 315 feet) deep. Because light does not reach the floor of most of the caves, it is possible that they extend much deeper than these lower estimates and widen below the surface. Dina is the only exception. Its floor is visible and was measured to be 130 meters (430 feet) deep. The interiors of these caverns may be protected from micrometeoroids, UV radiation, solar flares, and high-energy particles that bombard the planet's surface. Topic: Atmosphere. Mars lost its magnetosphere 4 billion years ago, possibly because of numerous asteroid strikes, so the solar wind interacts directly with the Martian ionosphere, lowering the atmospheric density by stripping away atoms from the outer layer. Both Mars Global Surveyor and Mars Express have detected ionized atmospheric particles trailing off into space behind Mars, and this atmospheric loss is being studied by the MAVEN orbiter. Compared to Earth, the atmosphere of Mars is quite rarefied. Atmospheric pressure on the surface today ranges from a low of 30 pascals (0.030 kilopascals) on Olympus Mons to over 1,155 pascals (1.155 kilopascals) in Hellas Planitia, with a mean pressure at the surface level of 600 pascals (0.60 kilopascals). The highest atmospheric density on Mars is equal to that found 35 kilometers (22 miles) above Earth's surface. The resulting mean surface pressure is only 0.6% of that of Earth, 101.3 kilopascals. The scale height of the atmosphere is about 10.8 kilometers, 6.7 miles, which is higher than Earth's 6 kilometers, 3.7 miles, because the surface gravity of Mars is only about 38% of Earth's, an effect offset by both the lower temperature and 50% higher average molecular weight of the atmosphere of Mars. The atmosphere of Mars consists of about 96% carbon dioxide, 1.93% argon and 1.89% nitrogen, along with traces of oxygen and water. The atmosphere is quite dusty, containing particulates about 1.5 micrometers in diameter, which give the Martian sky a tawny color when seen from the surface. It may take on a pink hue due to iron oxide particles suspended in it. Methane has been detected in the Martian atmosphere. It occurs in extended plumes, and the profiles imply that the methane is released from discrete regions. The concentration of methane fluctuates from about 0.24 ppb during the northern winter to about 0.65 ppb during the summer. In northern midsummer 2003, the principal plume contained 19,000 metric tons of methane, with an estimated source strength of 0.6 kilograms per second. The profiles suggest that there may be two local source regions, the first centered near 30 degrees north 260 degrees west and the second near 0 degrees north 310 degrees west. It is estimated that Mars must produce 270 tons per year of methane. Methane can exist in the Martian atmosphere for only a limited period before it is destroyed. Estimates of its lifetime range from 0.6 to 4 years. Its presence despite this short lifetime indicates that an active source of the gas must be present. Volcanic activity, cometary impacts, and the presence of methanogenic microbial life forms are among possible sources. Methane could be produced by a non-biological process called serpentinization involving water, carbon dioxide, and the mineral olivine, which is known to be common on Mars. The Curiosity rover, which landed on Mars in August 2012, is able to make measurements that distinguish between different isotopologues of methane. But even if the mission is to determine that microscopic Martian life is the source of the methane, the life forms likely reside far below the surface, outside of the rover's reach. The first measurements with the Tunable Laser Spectrometer (TLS) indicated that there is less than 5 ppb of methane at the landing site at the point of the measurement. On September 19, 2013, NASA scientists, from further measurements by Curiosity, reported no detection of atmospheric methane with a measured value of 0.18 plus or minus 0.67 ppbV, corresponding to an upper limit of only 1.3 ppbV, 95% confidence limit, and, as a result, conclude that the probability of current methanogenic microbial activity on Mars is reduced. The Mars Orbiter mission by India is searching for methane in the atmosphere, while the ExoMars Trace Gas Orbiter, launched in 2016, would further study the methane as well as its decomposition products, such as formaldehyde and methanol. During measurements lasting from April to August 2018, the satellite failed to detect any atmospheric methane, hinting at a new and hitherto unknown process by which CH4 is rapidly removed from the atmosphere in a short space of time. On December 16, 2014, NASA reported the Curiosity rover detected a tenfold spike, likely localized, in the amount of methane in the Martian atmosphere. Sample measurements taken a dozen times over 20 months, showed increases in late 2013 and early 2014, averaging 7 parts of methane per billion in the atmosphere. Before and after that, readings averaged around 1/10 that level. Ammonia was tentatively detected on Mars by the Mars Express satellite, but with its relatively short lifetime, it is not clear what produced it. Ammonia is not stable in the Martian atmosphere and breaks down after a few hours. One possible source is volcanic activity. In September 2017, NASA reported radiation levels on the surface of the planet Mars were temporarily doubled, and were associated with an aurora 25 times brighter than any observed earlier, due to a massive, and unexpected, solar storm in the middle of the month. Aurora. In 1994, the European Space Agency's Mars Express found an ultraviolet glow coming from magnetic